Welcome back. So the goal of today's video is to find the height of a fluid in tank 1 after its initial steady state is reduced to 80% at 100 seconds, and then find the height of the fluid at tank 2 if its initial steady state is raised 250% after 200 seconds. And so what we're going to do, all of these are the libraries that we're just adding things to or accessing things from. And so what we did is I just integrated or imported solve initial value problem from SciPy integrate, and then I accessed Jack's numpy and imported that, and I just imported that as a short of JNP, so I didn't have to type JNP or Jack's numpy every single time. And then we imported Jack's, so we have the ability to do import Jack's numpy. And then we did import make subplots from Plotly, so we had the ability to plot the functions that we're going to create and write up, and then eventually the sigmoid function, hopefully at the end. Hopefully we go through this where there's going to be a lot of shift enter and going back and things like that, so we'll see. And then what we're going to do is just import templates. We're going to make it so that way our plots come in with dark theme and they fit the entire theme of the collaboratory workspace itself. So what we're going to do now in this cell is just start defining the variables and things like numbers that we're going to need. So let's start with our end time for our thing. We're trying to reach the steady state of our second tank at 200 seconds, and that's the highest time requirement we have. So why don't we do 300 seconds as our end time? Let's do that the square root of 2g, or the acceleration due to gravity, is equal to Jack's square root of 2 times the acceleration due to gravity, which is 9.81. And then let's do, we have our cross-sectional area 1 is equal to the, I did it in parts A and B in the first video. It should be in this playlist, but it's equal to pi times the radius of the tank squared minus the height of the fluid minus the entire radius, that quantity squared. And after doing that with our initial radius of tank 1 being 5, I believe, maybe it's 4, I found that the cross-sectional area was 15 pi, and in order to be able to bring pi in, we do have to access Jack's numpy. And then for our cross-sectional area 2, I got that to be 3 times the Jack's numpy pi. And then we have our area of the pipe that connects tanks 1 and 2 is equal to 0.2 meters squared, and then the area of the pipe that allows fluid to leave the second tank is also equal to 0.2 meters. So we'll do that. See, this is why we shift enter and make sure everything is how we want it to be. Boom. So then we're going to bring in our initial height of our fluids, and in the first tank it is 5 meters, and then for our second tank, it is equal to 3 meters. And so what we want to do is define some of our just beginning equations that we'll use to eventually develop our functions and things like that. And so we have the flow rate, our initial flow rate from tanks 1 to 2 is equal to the pipe diameter from tanks 1 to 2 times the sign compensation that I spoke about in the last video of the initial height of tank 1 times the initial height of tank 2, or minus, sorry, times the acceleration due to gravity, SQ2G, that we defined earlier. It's a little bit easier than typing everything. And then the square root, square root of absolute value. That is a Jack's function as well, so we do have to call on that to bring that in. And we have our initial height of our fluid minus the initial height of our fluid in both tanks. And let's do shift enter and make sure that collaboratory agrees with that. It does. And then we have that the initial flow rate of our first tank is equal to the flow rate of the fluid in the pipe. So we have our first tank, and then there's the little pipe, and the second tank. and the flow rate into the first tank is equal to the flow rate out of the first tank, pretty much. And then we have our flow rate of our second tank initially out is equal to the area of that pipe that lets fluid flow out times the acceleration due to gravity, SQ2G, which we again defined earlier, times the square root of the height of our fluid in our second tank. And I think it might disagree with me here. Yep, that's what I thought, because we needed to be our initial condition. And then from here, we can say that the flow rate into our second tank initially is equal to the flow rate out initial minus the flow rate into the second tank from the first tank. And now going from here, we can say that what we want to do is to define let me do this real quick. That'll come in later. We want to define two functions that allow us to set our, or explain, or display, or portray our flow rate as a function of time. And so what we want to do is we're going to define our flow rate in as a function of time, colon, and we want to return that. And we'll say, we'll just do it like this right now. We said it's going to be 80% of its initial value. And so let's do our initial value. And then we want to define our, nope, not capsule, our second flow rate in as a function of time. And we want to return that as, and what was it, 250, ooh, I cannot type, 250% increase in our flow rate from our initial state. So let's do that. Perfect. And so what we want to do is with our IVP initial value problem, we want to define a function with the right-hand side of an equation, but in order to do so, we have to remove the I, or the initial condition, from all of our values, because that removes the steady state from it. And to do so, what we want to do is we wanted to define it as the differential height with respect to time, and we want that as a function of time with respect to height. And so what we're going to do is we're going to say that our height of our first tank is equal to 0, and then we want the height of our second tank is equal to 1, or state 1. And then make sure it agrees with that. Why? Oh, see? Colon. Always got to double check. Then from here, what we're going to say is that the flow now, not steady, or no longer steady state, from tank 1 to tank 2 is equal to the area of that pipe, area of that pipe from tank 1 to tank 2 times the sign compensation of the first height, not initial anymore, minus the second height, times the acceleration due to, or the square root of the acceleration due to gravity, times the square root of the absolute value, again calling on absolute value from Jack's numpy, of the first height minus the second height of the fluids in their respective tanks. Make sure collaboratory agrees with that. It does. And then we're going to say that the flow rate out of our second tank is equal to the area of that pipe that allows fluid to flow out times the square root of the acceleration due to gravity times the square root of the second height in the second tank. And once that is complete, what we want to do is return an array of all of the values of the flow rates divided by, or no, sorry, all of the values of the flow rates that we just set up, sorry, the function dH/dt. And so what we want to do is return J and P array, and we want to return that as, we have our flow rate in as a for the first tank as a function of time minus the flow rate out divided by the cross-sectional, let me put this in parentheses again, divided by the cross-sectional area of tank 1. And then we want to have the flow rate of tank 1 as a function of time plus the flow rate out from tank 1 into tank 2 minus the flow out of tank 2 alone divided by the cross-sectional area of tank 2. Cool. So now that we have this complete, we already defined our t end as 300 seconds. So since we want to find our height of the fluid at 200 seconds for the second tank. But now we can set up our initial value problem. And so what we want is we want our result, that will come in just a sec, I'll explain, equal to the solve initial value problem, not two underscores, initial value problem of the function that we want it to be is dh dt. And we want that to go from time 0 to our end time, not a capital T. And then we want that to be using the heights of our initial in tank 1 and then our initial height in tank 2 as our reference points. And we want to solve this using the Radow method, which is just a method for solving differential equations. So we're going to say method equals Radow, or Radow, however you want to say it. And then we want our dense output to equal true. Okay, so collaboratory like that. And so now what we want to do is, let me do this. So if I shift enter this cell, what it does is it gives us the values for our heights of our fluid, sorry. And so what we want to do is be able to solve for any height at a specific time using this initial value problem. And so we're going to use the solution field. But what I want to do is, let's say res equals, shift enter that. So it's going to remove that array just from our view, but like it's obviously still there. And so we need to define our time plot, and that is equal to the spacing from 0 to our end time to 301, because 0 to 300 is 301 total points. And so we want that, and we'll make sure collaboratory agrees with that. It does. And so we want to say that our solution is equal to the result of the solution of all of the times on our time plot. And so then we're going to say that the solution 0 is equal to the, actually I'll put that in a different cell, sorry. So then our solution 0 is all of the heights of the fluid in the first tank during our time span, which is 300 seconds. And then, can I collapse this? Okay, cool. And then our solution 1 is all of the heights of the fluid in our second tank during our 300 seconds. And I'll collapse that too. And so now what we want to do is we want to plot all of these. So we want to say figure is equal to make underscore subplots with rows equal to 1 and columns equal to 1. Maybe no spaces. And then we're going to add the plots that we want. And so we're going to graph objects on a scatter plot. And we're going to say that our x axis is all of the points on our time plot from 0 to 301. And then our y-axis is equal to our heights for our first tank over those 300 seconds. And then we will name this, we'll just do tank 1 height, and we will put that on 1 column equals 1, and then we will copy and paste this down here, and we'll do the same thing but with our second set of heights. And let's see if we get a plot. We did. Good. So then what we can do is we can set up a second column, and we can do the flow rates for each of our tanks. And so what we'll do is I'll just paste this down here. So instead of our heights, which we had set to solution, what we can do is we can say that this is equal to our flow rate for our tank 1 in as a function of our time plot, and we'll put that on column, can you scroll over, 2, and then we'll do tank 1 FR for flow rate. And then if I copy this, oh god, come on, and paste it, and then we'll do flow rate of our second tank in, and we'll do tank 2 flow rate. Let's see if they go in together. It didn't. That's fine, but we know that it works for our first one. So what I'll do is explain that if we wanted to have our plot oscillate, then what we can do is rearrange these equations in a way using sine. And so what I'll do is I'll say that instead of 80% of our initial flow rate into tank 1, what we can do is we can say that our initial flow rate into tank 1 plus that 80% reduction of our flow rate into tank 1 initially times the sine of 2 times pi times our entire time that we're looking at, which is 300 seconds, divided by our end time. And then we can copy that, put that down here, and change this to 2, and then 2.5 for our 250% increase, and that should work. And return. 1, 2. Simple mistakes. Sure, there we go. So I'm not sure why it did that to me, but it did. So on our left, like I said, we have the height of the fluids in our tanks as time continues for both of our tanks. And then on the right, we have our flow rates as time increases using an oscillating function. And so what we're going to do is I left this cell blank for a... Okay, go away, please. Thank you. Wow. Whew. I left this cell blank for a reason, because what we're going to do is we can incorporate a sigmoid function into this plotting scheme. And so what a sigmoid function does is basically takes a number from the range negative to positive infinity and squashes it down in a graph from the range 0 to 1. And so what I'm going to do is I'll define a function, and we'll call it switch. And we will go from our time, like any of our time values, with value 1 and value 2, and we'll call it t-switch because it does depend on time. And we'll have a scale, colon, and then what we'll say is we'll bring in Jack's neural network of the sigmoid function of our time minus the time we want our switch at, divided by the scale of our graph, times the second value minus the first value plus value 1. And let me put that in another set of parentheses so I don't break anything. Boom, boom, boom. Cool. So that's closed in. And so what we can do is we can then change these flow rates to the desired time that we want. And what we'll do is we'll say that we want our flow rate using our switch function at a specific time t with our initial flow rate at 1, and we want our 80% reduction of our flow rate, our initial flow rate at 100 seconds, which is where we want our value. And what we don't want, actually, I'll do it right now, actually. So we'll set the scale to 1. So we'll do the same thing, and I'll explain the scale issue in just a sec. Q our initial flow rate for our second tank, and we want our 250% increase. And we want that at 200 seconds. And we might have to play around with our end time. I'm not really sure, because we're about to find out. So this might take another second. Oh, it's done. Oh, good. Yeah, I love that. Oh, where are we? Boom, boom, boom. Perfect. So our scale being 1 is too drastic because that's not realistic. And so what we're gonna have to do is we can do, because it's what we basically graphed right here is a step function. So what we can do is we can change our end time. If these don't go away, I'm going to freak out. So let's change our end time to, we'll do 1,000 seconds. So then these will stay the same, t end, and we need to go to 1001. That won't change, that won't change, that will change. And then let's change our scale to, let's do a scale of 25, and we'll see if that looks a little bit better. So the runtime, we'll just restart and run all. And that way it can just reset, incorporate all the new values. I don't have to shift enter, shift enter, shift enter, shift enter the whole way down the table. Return unsupported. That is unexpected. Let's see. Unexpected indent. Okay, that's fair. Okay, well, I don't want to lose that. Where? Unsupported. Return. Maybe it's a spacing issue? Interesting. Yes, I am aware of that and this. That is confusing. I'm not sure, but we did get the sigmoid function to work. So why did you decide to do this now? What if I did this? Okay, so it's definitely this line's issue. Return Jack's array. Huh. I cannot believe that just happened. There was not a single issue. Return. But it worked when they were 1? Supported. But that's interesting. We got the sigmoid function to work. I'm not entirely sure why, but it decided to just poop out on me. But yeah, that I don't know. Thanks for watching.